So, dear learners, this week too, we are going to see the third PPT termed as quantum circuits. So, we are going to have a basic insights of how we are going to deal with the quantum circuits in quantum computing field. So, session outcomes are we are going to deal with definition of quantum circuits, multi-qubit gates, measurements and state collapse, quantum gates, role and gates, gate structure, controlled and not, its operations, simple Hadamard gate, poly X gate, poly Z gate, Qiskit circuit formation with IBM provider. So quantum circuit, it is none other than a circuit which is holding a sequence of quantum gates applied to qubits. Qubits can be in superposition states with zeros and ones simultaneously. Gates are unitary operations like rotations or flips. Unlike classical logic circuits, quantum circuits are reversible, meaning the input can be recovered from the output. Circuits are read from left to right, representing the chronological flow of time. So this is a simple definition and simple working visualization of quantum circuits. Multi-qubit gates. Controlled NOT flips the target qubit if and only if the control bit is going to hold the following, creating entanglement states. Exchange the states of two qubits. Tophaly, that is controlled C0, the 3 qubit gate that flips the target if both control bits are. It's universal for classical reversible logic circuits. So measurements and state collapse of formation of quantum circuits is as follows. Meter symbol. This represents the transition from quantum information to classical data. Probabilistic outcome. Measurement collapses a superposition into a definite classical state 0 or 1 based on the square of the state's amplitudes. Irreversibility. Unlike gates, measurement is a non-unitary operation that can't be undone. Quantum gates. Quantum gates are similar to classical logic gates but operate on qubits using quantum principles. Examples, this includes Hadamard gates for superpositions and controlled gate for entanglement. We all know what is entanglement and what is measurement. Entanglement is a core feature of quantum circuits where qubit states are interlinked even across vast distances. Measurement is concluding our quantum circuits. Measurement collapses qubits from superposition to classical states 0 or 1, providing the computational results. Roles and gates. Role of quantum circuits. Quantum circuits show promise for specific computational problems like factoring large numbers, cryptography, optimization, simulating quantum systems. Universal quantum gate is nothing but it is going to perform a wide range of quantum computations. A quantum computer must have a set of universal quantum gates which is similar to classical logical gates. Gate structures with example. Example of Hadamard gate acting on one qubit which is going to hold H, which is going to hold a control line and a single target line. Example 2 of NOT gate acting on one qubit but it is going to hold two sort of information. One is with bracket, one is ket. So example of controlled NOT gate is going to hold the single logical M state which is going to hold the two target lines as shown in the figure. So controlled NOT gate. Symbols for quantum gates are used on the quantum circuits. Hadamard gate, for instance, is indicated by H, whereas the C0 gate is depicted as a cross with control and target qubit. So always if you are going to hold two sort of inputs in terms of ones and zeros, you are going to get this sort of answers in terms of ones and zeros, where we are going to hold half composition in terms of plus and half composition in terms of minus answers. Operations. So gate operations, the arrows connecting the gates to qubit lines indicate the application of quantum gates on specific qubits. The direction of the arrow signifies the temporal order of operations. Superpositions and entanglement. Quantum circuit diagrams depict the operations like superpositions and entanglement. Superposition is visually represented as gate splitting the qubit line, while entanglement is shown as the line connecting qubits indicating their entangled state. Measurement means quantum measurements which collapse qubit states into classical outcomes are represented by a open circle at the end of qubit line. So this is sample with ket 0 and ket 1 an amplitude frequency where you are going to get both the answers in terms of zeros and ones. So the Hadamard gate is a crucial quantum gate. It puts a qubit into superposition of states. When applied to a qubit initially in the state of 0, it transforms it into this sort of state, making it equally likely to be measured as 0 or 1. Poly X gate, also known as the quantum NOT gate, Poly X flips the state of qubit, applying X to this resulting in 1 and vice versa. Poly Z gates, these gates introduces phase changes in the state of qubits. They manipulate the complex components of quantum states in terms of Y, in terms of Z. Controlled NOT gate. The control NOT gate acts as two qubits, a control qubit and a target qubit. If the control qubit is in 1, it applies an X gate to the target qubit. Otherwise, it does nothing. This gate is crucial for creating an entanglement, a key resource in quantum computing field. Control NOT gate acts on two qubits, max representation. So, Qiskit formation. To build a quantum circuit using Qiskit, you can follow this example, which creates a simple Bell state. The fundamental state where two qubits are maximally entangled. So first four lines which states that from Qiskit import quantum circuit, from Qiskit visualization import plot histogram and air simulator. So these three lines are useful for importing this quantum inside the quantum libraries inside the quantum simulator. So whenever we are going to execute any sort of application based on this quantum simulators, so we have to follow this sort of rules. So when first step is step 1, first step is we are going to depend upon a quantum simulator where you are going to import this information to create quantum circuit, to plot the histogram, to depend upon any sort of hardware. Here the hardware which has dependent on is air simulator. So the code snippet is demonstrating you are going to create a simple quantum circuit with two qubits and two classical bits to measure the results. So first line, three lines are for importing. So then next we are going for circuit is equal to quantum circuit 2, which is nothing but creating a quantum circuit with two qubits and two classical qubits. And next line is Hadamard gate creation, applying the Hadamard gate H to qubit 0. The next line is applying controlled NOT gate with control qubit 0 and target qubit 1. So this is termed as an entangled qubits. The next one, circuit.measure is for measuring the qubit 0 and 1 to classical bits 0 and 1. So this is the explanation. So quantum circuit 2 of 2, it is initializing a quantum circuit with 2 qubits and classical with 2 bits for measurements. The next line is application of Hadamard gate to qubit 0, putting it into superposition state of both 0 and 1 simultaneously. That is a measure. So circuit.cx is going to throw applying control NOT gate, entangling the qubit 0, that is control line with the target line, which creates maximally entangled state of Bell. So measure is going to throw some sort of measure in terms of storing the result with 0 and 1. The purpose of this is to demonstrate by creating a Bell state where two qubits are maximally entangled. It is a fundamental example in quantum computing for exploring superpositions and entanglement. Next step is we have to run the circuit using the simulator. For this we have to pick a simulator. So here the simulator is termed as air simulator to get the measurement result. Then for running the circuits and getting the result, we are going to depend upon job is equal to simulator.run of, where in the parameter we are going to pass circuit and shorts nothing but the epochs, or you can call it as iterations. Whenever we are going to improve the shorts, the result is going to be in higher level. So we are going to store the result information into the result variable. So visualizing the result with the plot histogram also can be done. The next one, do you want some sort of counts? Means we can also identify how much amount of count it is going to throw for us in terms of simulations. So that is the next level. So if we are going for this particular hardware, we will be holding some sort of information in terms of creation, visualization, picking of simulator at the background, and getting the counts. So Python code is probably commercially used, which is used for creation, simulation at the back end. So this sort of simulator is provided by Qiskit Air for executing quantum circuits, which holds the provider named as IBM. So the print statement displays all the counts. So in short, this code simulates quantum circuit on air simulator, which runs 1,000 times and print the measurement informations, that is statistics. So this is a simple quantum circuit with a formation of 2 qubits with the measurement output in terms of classical bits of again 2. So I think learners, you could have understood a basic idea of what is creation of quantum circuits in this particular session. So thank you for your listening. So these are all the performance metrics: circuit width, circuit depth, then gate count. These are all things we can give. So minus is that we will be holding some sort of noise in terms of intermediate scale quantum, and decoherence will be measured, which is none other than the latency, which is going to be thrown out. So these are all the common performance metrics whenever we are going to deal with quantum computing projects. Thank you all.